recording. I record all of these. You can minimize that gray control panel. You don't really need it anymore. You don't want to close it out. That'll close out our session. But you can shrink it up by clicking on that orange rectangle with the white arrow in it.
Right.
It acts as a toggle switch, and it minimizes it and expands it. So if you minimize it, it opens up a little bit more of your computer screen.
Right.
Okay. So I got this document. Whoops. Hold on a moment. Yeah, clicked on the wrong thing. I got the document you sent me.
All right.
Now, a couple of things. Did you use your iPhone? Do you have a new iPhone?
Yes.
Okay. Is it an iPhone 6 or 6?
Yes.
All right. I know that the resolution is terrific on those things, and yet the resolution on this document that I got is not that good. As you can see, it's difficult to read. For tonight's session, this will work just fine because you can clarify some of these things for me.
Right.
Either two things happened. One is because you sent it to my telephone and then I had to forward it to my computer, I lost resolution.
Okay.
The other possibility is you might have the resolution set on a low setting.
I can change that?
Yeah, with most phones. I don't have an iPhone, so I can't specifically tell you how to change it, but it's changeable. When you take a picture, make sure you set it on the highest resolution, and I suspect that is what happened. But also in the future, if you would send pictures to my email address as opposed to my phone number, then that will eliminate that other possibility.
Okay, since when I first sent it, it said that there was a problem when I sent it.
Okay.
So I had to resend it.
Okay.
But the pictures that I have are high resolution.
I'm sure they are. I know the camera is excellent on those. In fact, any camera would be excellent. What we're looking at here would be something from like a camera from 10 years ago. But like I said, we can handle it for tonight without any problem because I can make these out. In other words, this first problem here is f of x equals 3x minus 8?
Yes.
Okay. You want to start here with number 4?
Can we start back at the beginning since I sent a total of 3 pictures?
I only got 1. That was the problem. Are the other problems stuff you can verbalize? As long as they're not based on a graph. Let's start at 1. What is 1? What do they want you to do on 1?
Okay, so the homework assignment is called series and sigma notation.
Okay.
So on question 1, my teacher had me do, he gave us the series of steps in order to figure out how to
write the sigma notation for a given series?
No, how to write the series for the given sigma notation.
Okay, so what's the sigma notation?
Okay, so I already have done the first 4.
Okay.
But on 1E, it goes sigma k equals 0 underneath, and then 6 up top, times sine times the quantity of pi over 6k.
Like that, or the k is in the denominator?
Like that.
Okay. Okay. Sigmas means sum.
Right.
So we have 7 terms in this series, right? When we go from 0 to 6, we're going to end up with 7 terms. So what's the first term? Let's just list them.
0.
List them like that. Because when we substitute 0 for k, the sign of 0 is 0. Okay. What's the second term?
Well, the second term is 1.
K is 1. So now we're taking the sine of pi over 6. And what's that value?
That would be... Oh, I'm in the wrong mode.
Okay.
1/2.
Okay. Now, are you supposed to use your calculators on this?
He did not specify.
The only reason I'm doubting it is because these are angles that you can figure out without a calculator, and in fact you should be adept at figuring them out without a calculator, at least in a trig class. Now, your class is going to be a little different because it's an IB course, so I'm not quite sure what you've learned and what you haven't learned. Are you comfortable with going back and forth between radians and degrees? In other words, do you know what pi over 6 is in terms of degrees?
Yes, 30 degrees.
Okay. And so if the way I do this, and tell me if they've taught you different, hold on a moment, is we have our two special triangles, 30, 60, 90, which are dimensioned like that, and then we have our 45, 45, which is dimensioned like that. And from these two triangles, you can figure out all of your first quadrant trig functions for any multiple of 30, 45, or 60. Okay? So the reason the sine of 30 degrees is 1/2 is because of this triangle. It's opposite over hypotenuse.
Yes, they've mentioned it this way when I first learned the unit circle.
Okay.
But now they're recommending a more faster way of saying how
Just use your...
sine and cosine can only be a certain possibility. They went 0 divided by 4, 1 divided by 4, 2 divided by 4, 3 divided by 4, and 4 divided by 4, and then square rooted everything.
Okay, I'm not quite sure what that's coming from. But the sine of angles can be anything from -1 to 1. In other words, let's look at a graph of the sine function here for a moment. If I'm labeling this in radians, that's 2 pi. That's 1. That's -1. This is pi. That's pi over 2. That's 3 pi over 2. In other words, I've taken my unit circle and broke it up into its 4 quarter points. So I can get any value I want from the sine of an angle, as long as it's between -1 and 1. It does not have to go in increments of 1/2 or 1 or anything. In other words, I can find an angle where the sine is equal to 0.3 right there. I can also find an angle where the sine is equal to 0.9 right there. You with me?
Mm-hmm.
Okay. So I'm not quite exactly sure what you meant by your previous...
I mean, like,
But...
it's so much easier if I could show you. So, what they pretty much did is that the only possible numbers for sine and cosine for the special angles is 0.
Okay. Now I'm with you. The special angles being 30, 45, or 60, or 90.
Right.
Okay. Well, these two triangles give you the same thing. In other words,
yeah, they just prefer it the other way since it's faster.
Okay, these two triangles are fairly basic. You've been taught them since Algebra 1, so you get taught these two triangles in algebra, geometry, and trig, and you can always use these to figure out the sine of any of these angles. So let's figure out the third term. When k is equal to 2, what is the sine of pi over 6 times 2?
The sine of pi over 3.
It's square root of 3 over 2. In other words, the sine of pi over 3 is the same as 60 degrees, and that's square root of 3 over 2. Okay. When k is 3, what are we looking at?
Sine of 1/2, so...
Or the sine of pi over 2.
Right.
Okay.
Pi over 2 is 90 degrees.
Right. So it's hard to get that from those two triangles, but if you have this memorized, this is 90 degrees right there.
Right.
So it's 1.
So 1.
So that's the fourth term. How about the fifth term? That would be when k is equal.
Sine of 2 pi over 3, which is... It would be 120 degrees.
Which is, what's the value of that?
Negative 1/2.
Okay.
Wait, no. Sine is...
Sine is positive in the first and second quadrants. Sine is positive all the way up to 180.
So root 3 over 2.
Square root of 3 over 2. In other words, it has the same value as the sine of 60 degrees. And then finally, the sixth term, which is when k is equal to 5.
The sine of 5 pi over 6.
Okay.
So that would be 150 degrees.
Okay.
So 1/2.
And finally, the last term, the seventh term, where k is equal to 6. We're taking the sine of pi, and we can see from our graph that that is 0. So that last term is 0.
Right.
So there is a symmetry here, you'll notice.
Yes.
Based around 1. So we have 1, 2, and 2 of these square root of 3 over 2, which becomes a square root of 3. So what is this equal to? 2 plus root 3. So that's the answer for the total. When you take sigma, you're always adding every term.
Right.
Okay? And I don't know if that's the answer they want, or they want you to convert it to a decimal. This is actually the preferred answer, 2 plus root 3.
Right.
Okay. What else you got?
So for the last part for this question, it says sigma k equals 1.
I'm sorry, I didn't hear something there. It says what?
Sigma k equals 1.
Oh, okay. I'm sorry.
K equals 10. Then 2,520 over k.
Like that?
Yes.
Okay. How are we going to do this?
I personally make a row of numbers for the index variables. So 1 through 10.
Okay. So we're going to have 10 terms.
Right.
Okay. First term's going to be what?
2,520.
Second term is going to be what?
1,260.
Third term?
840.
6. Looks like 630 to me. Oh, excuse me. We're not cutting it in half every time. Okay, so you can do this one then. You're just going to have 10 terms, you add them up. Do you have answers for these?
No.
Okay.
We go over them in class.
Okay, well, it's clear to me you know how to do this one. So it would just be kind of a waste of time for us to go through the arithmetic of coming up with this number. We're probably better off setting the problem up, making sure you know how to do it, and going on. Especially since we only have like a half an hour to work. Okay? So
that's question number 1. Question number 2 is finding the sigma. So they give me the
to give you the series?
Yes, they give me this series.
Okay.
And I have to find the sigma.
Okay, what's the series?
For the first one, it's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6.
Is that it?
Yes, and this one, I'm pretty sure I can do in my head.
Okay.
Since
what is it?
I would think that it would be sigma k equals 1 and 6, and it's 1 over k.
That's correct.
Right.
Okay.
Then after that, they start...
These can be kind of tricky. That one was very basic, but do you have another one?
Yes. 42 plus 52 plus 62 plus 72 plus 82 plus 92 plus 102 plus 112.
Is that the last term?
Yes.
Okay. So,
so what sigma could be, so sigma k equals,
let's see if we can figure out what goes inside here first.
Alright, so it could possibly be 32 plus k of 10.
That works. K going what?
From 1 to 8.
Right. Now, these aren't unique. In other words, I could have also come up with this. Notice that this gives you the same series.
Right.
And who knows how many other possible sigmas you could come up with. So there's not a unique sigma for a series. There might be for some series, but there's lots of series where you can have multiple answers, multiple sigmas. Okay. What else you got?
Okay. The next one, since the others are similar,
okay.
The next one that's different is 2 to the 7th plus 2 to the 8th plus 2 to the 9th plus 2 to the 10th plus 2 to the 11th plus 2 to the 12th. I mean, that one I could also have the sigma k equals 7 and then k equals 12 and then have 2 to the k.
That's all there is to it. And you could also turn this around if you wanted it to go from k to the 1. then something like that, 2 to the 7 minus k, and then you could alter what k goes to. But there's nothing wrong with k going from 7 to 12. These sigma notations don't always go from 0 to a number. Sometimes they go from 1 to a number, sometimes they go from 2. But basically, there's no restriction on those numbers.
Right.
Okay?
Okay.
What else you got?
Then for F, he gave me a hint. This formula is so simple, some students will find it difficult to write the function, but it's a simple function.
Okay.
And it goes 1 plus 2 plus 3 plus 4, etc. till plus 100. So I believe sigma would be k equals 1 to 100 times k.
That's it.
Alright. And the next one is essentially the same, except it's going by increments of 5.
Okay.
So it's the same concept, so that I can do myself.
So 5k is probably what goes in there.
Yes.
Okay.
And then question number 3 is just an expansion that I can do.
Okay.
Then we're on question number 4.
Okay. And that's what I'm looking at on this diagram?
Yes.
Okay. Inverse functions. There's only 2 things you need to remember on how to write an inverse function. First of all, you probably want to write it as y equals a function of x instead of f of x.
Right.
Just makes it a little bit easier. There's 2 steps. You can do them in either order. My favorite way to do it is switch the variables as step 1 and then solve for y. Is that the way you do it? Because you could do it the other way. You could solve for x and then switch the variables. You get the same answer.
What do you mean switch the variables?
Okay, let's go through it on this problem here. I've got a y and an x. I'm going to switch them. I'm going to make it x equals 3y minus 8. And then I'm going to solve for y. So y becomes that. And there is your inverse function. It's very simple. And I could have done it the other way. I could have solved this for x, where x is equal to y plus 8 divided by 3, and then switch the variables. It doesn't matter which order you do them in. I do think a lot of math is based on memorizing stuff in a systematic way, and so I do think it's a good way to always do it one way or the other, just for memorization sake. And then if you want, you can replace that y with f inverse of x. In other words, that now becomes that.
Sorry, but I've just never heard of switching the variables.
It's actually a very simple technique to learn. And the only way I actually know how to do inverses is that technique. By switch the variables and then solve for y. Because usually you're given a function as y equals something. Or f of x equals something, same thing. And that's what we're given here. So we really want to solve for the other variable. And I suppose that's all you really need to do. You could say solve this function for x, and that is the inverse. But the typical way that it's taught in the Colorado school system is switch the variables and solve for y. Or solve for x and then switch the variables. Either order works just. There's no real difference. But at some point you want to switch the variables.
I've just never heard of it that way, or just, it's, okay.
Okay? So this works really well for simple functions. Doesn't work quite as well when you have like quadratics. If this were a quadratic function, it would be much harder to solve. And I would be surprised if they didn't give you that at some point, given your IB program.
Right.
But if we're not dealing with that tonight, probably not worth going into.
All right.
Let's look at some of these derivatives. Or what we got about 5 minutes here. What would you like to do with the rest of the time tonight?
You see, I can do derivatives quite well.
Okay.
I am comfortable enough with 6.
Okay.
That I can do it. I feel that 7 I probably would have the most difficulty.
All right, let's look at 7. To make sure it's hard for me to read that. What is the bottom limit?
X equals 2.
Okay, so this goes from 2 to 4.
Right.
And we're doing natural log of 3x plus 5 dx.
Right.
Okay. If we use substitution, what are we going to let u equal?
I would say u equals 3x plus 5.
Yeah. And the reason is that we know how to integrate that.
Right.
So if I let, the problem is if we're going to turn this integral into an integral of u as opposed to an integral of x, then we need to also substitute for dx. Well, what does du dx equal to?
3.
So du equals 3 dx.
Equals...
So now there's a few ways to look at this. I think that this is a good way for starters. If you're not familiar with substitution, let's do it all the way down to that step there.
Right.
Now I can rewrite this whole thing as natural log of u, and in place of dx, I'm going to put du over 3 from this step here.
Alright.
Okay. Now we have an integral that is an integral of u, not x anymore. So our limits of integration, I can also do this 2 different ways. I can change them immediately. In other words, I can tell that as x goes from 2 to 4, u goes from 11 to 17. So I could do it this way if I want. And now this is the same as that.
Right.
Okay. Well, let's do this integral. We can take the 3 outside the integral. What is the integral of natural log of u?
Hold on.
It's 1 over u. It's kind of a special.
Right.
You can't.
Right.
Yeah, it's the one that's a little special. In other words, when you're integrating, or when you're, hold on a moment.
No, sorry, I'm just not used to the changing the limits immediately.
Well, you don't have to. You don't have to. And let's not. As I said, there's 2 ways to do it. So let's leave those limits blank. If we had to fill them in, they would have to say 11 to 17. Okay? But we're going to leave them blank for the moment. In other words, what we're going to do is do this integral, and then resubstitute back for u, and then we'll be able to do the evaluation based on the original limits. And a lot of people do find that easier, and that's fine.
Alright, yeah, since that's what I was talking about.
Okay. Hold on one moment. Just a second. What happened to my calculus book? So, the integral of the natural log of u
Would be 1 over u? Well,
no.
technically it'd be du times 1 over u.
Here's the
It
thing.
would be
If I
changing.
take the derivative of the natural log of u, I get 1 over u. So the integral of 1 over u is the natural log of u. But the integral of natural log is not the same as the derivative of it.
Right.
So this is not one that I have memorized right off my top of my head. In fact, I can't believe it's not on the first inside page of my book. That's why I was looking for it. Hold on, I'll get it real quick here.
Alright. Since I think beforehand I was just told to keep the natural log.
To do what?
Keep the natural log. It's something. Yeah.
Oops, hold on a second here. Just a second.
No, I'm waiting for them to do something.
Didn't like my natural log. It's telling me the integral of the log of x dx is x log of x minus 1 plus a constant. Okay, so this is an odd thing to give you, the natural log, the integral of the natural log. All right, well, based on that answer.
I mean, often what he has us do is have large brackets, like the function equals like a bracket with the borders, and then natural log of, and then like substituted back, like in parentheses 3x.
Well, let's assume that the integral of natural log of x is x times natural log of x minus 1. Okay, I think that's probably a fair assumption. In other words, our problem is the integral of the natural log of u, du, with the 1/3 out there,
Right.
And I'm going to assume that that's 1/3, and this would be u times natural log of u minus 1 plus c. And our u is 3x minus 8. Is that what it was? What was it?
Right.
3x plus 5.
Oh.
I go back and I
sorry,
substitute for that u. And then the c I don't need because we're actually dealing with a definite integral. So I'm going to evaluate this thing from 2 to 4.
Right.
And do you know how to handle these evaluations?
You plug in the limits.
Plug in the top number first.
Right, and then subtract it with the bottom.
So the way this would play out would be 1/3 times 17 times natural log of 17 minus 1.
So,
and then subtracting. When I plug in 2, I get 11 times natural log of 11 minus 1. Okay. Now, they wanted the answer as a natural log function.
Right.
So let's see. We can simplify this thing. Let's see. If I multiply this whole thing out here, I get 17/3 times natural log of 17 minus 17/3 minus 11/3 times the natural log of 11 minus 11, excuse me, this was 1, let's see. No, because it was 17 times the minus 1 times the 1/3. So that minus 17/3 is correct. And then 11, that's also correct there.
Wait, wouldn't the natural log also be divided by a 3? Oh, wait, no, I see it now.
I'll
Okay.
get to it. I'm leaving the 1/3 out just to make it a little simpler at this point. Okay, so now we have this. Well, we could combine this part. So what do we have? We have 17/3 natural log of 17 minus 17/3 plus 11/3 is minus 8/3. And so our number is minus 8/3. And this becomes minus 11/3 natural log of 11. And natural log of 17 minus natural log of 11 is, how do you combine that?
I haven't done natural logs.
They're the same as regular logs. When you have the log of A minus, if you have the log of A minus the log of B, that's equal
It's divided.
Yeah, that's equal to the log of A over B.
All right.
Okay. So, whoops. Also, when you have the natural log of a to the b power, that's equal to b times natural log of a.
Right. I know the law.
So I can take that right there and make that the exponent. In other words, I can turn this into the natural log of 17 to the 17/3 power minus the natural log of 11 to the 11/3 power minus 8 over 3. And that becomes natural log of 17 to the 17/3 divided by 11 to the 11/3 minus 8/3. And that's probably the form of the answer they want for this problem.
Oh, I don't know. I mean, I've never seen it like that before.
Well, only because they say in the problem that leave the answer as a single logarithm as opposed to a number. In other words, they don't want us to convert this to a decimal because then our answer would be as a number.
Right. No, it's being done in a different way that I'm used to.
Okay. Well, that's going to happen from time to time as we work, and I'm fine with teaching it to you the way you were taught how to do it, and we can certainly do that when that problem comes up. We're probably, this is a good spot to stop for tonight. And I don't know that this is the exact answer just because there was a lot of arithmetic here that I went through rather quick. So I could have made a math error here. And I also started with the assumption that the integral of natural log of u was u times natural log of u minus 1. But I think this is the answer. And you're going to do b in essentially the same way. You're going to let u equal cosine x. The real key on doing these problems by substitution is over here on the right side.
Right.
In other words, let u be the complicated function that's messing everything up, and then always solve for du dx, and then always figure out what dx is.
Right.
In terms of that, and then you can go into the original integral and turn it completely into an integral of u instead of an integral of x. And then once you integrate, go back, resubstitute, and once you've done that, you can evaluate it at the original limits. It isn't actually necessary to do that other step. In other words, if I wanted to solve this problem from 11 to 17, I could do it totally and I would not ever have to go back and resubstitute. In other words, I can solve it from this step here, where I use my limits of integration are 11 and 17 instead of from 2 to 4. And that's a perfectly legitimate way to do it. And sometimes when really, really hard integral problems, that's the best way to do it, is to use the new limits of integration.
All right.
But you can generally do it either way. Okay. Your mom mentioned in her email, or you did, I guess, when you scheduled, that you wanted Thursday night regularly at this time?
Yes.
6 o'clock for a half hour?
Yes.
I'll do it.
Yes.
You got this spot until further notice.
All right.
Okay? So I'll talk to you next Thursday, and take a look at your camera settings. I have a feeling you might have it set not on the highest resolution. Oh, it could have just happened because you went through my phone instead of my email address. Let me give you the best email address to send it to. It's not actually the one that's listed on Digital Math Tutor, although that works. It just takes an extra minute for me to get it. So it depends on how far in advance you're sending it to me. If you want me to get it the quickest, this is the email address you want to send it to. And this is the one that's on the business card that I gave your mom.
All right.
And then that might solve the problem. It might not be your setting is incorrect on your phone. It might just be that going through my phone and then having to have me forward it to my computer is what messed up the resolution. We'll find out next time, I guess. Okay?
Okay.
All right. I'll talk to you next Thursday. Now, next Thursday is all I'll do is I won't call you. I will text you the meeting ID number. And that changes every time, okay? In other words, even if I had a session in 10 minutes, I'd have to change that meeting ID number for that student. So it's always going to change, and I'll just text it. So the number that I call that you have listed here, this is the best one to text it to, the 6929?
Yes.
Okay, that's what I'll always do it to that, and I'll put this number as your number into my contacts list, and I'll always do it that way.
Okay.
Okay? All right, Diana.
Okay.
Have a good day or a good evening, and I'll talk to you next Thursday.
All right.
Bye-bye.
Bye.